for Dr. Angelina Frank, Head of Science and Technology APAC at Kai Ventures, moderating the session. Let's give her a round of applause. Over to you.
Great. Hello, everyone. It's an incredible honor to be here with a panel such as this. I am awed by the panel. I am equally awed by the audience. Today will be an amazing occasion to probe together what kind of applications we can see that Quantum has produced today. What is the state of the industry with respect to NISQ, with respect to transition to fault-tolerant quantum computing, and where do we see now, from the angle of very different software companies, quantum software companies, where do we see the kind of key innovations and applications looking forward, and the key value statements. And with that, I am very honored to welcome our 4 guests today. And I would love for Joe maybe to begin with a brief self-introduction.
Sure. I'm Joe Fitzsimons. I'm the founder and CEO of Horizon Quantum Computing. What we're doing at Horizon Quantum is to try to build the software infrastructure to enable developers to take advantage of quantum computers to get to a real quantum advantage, to get to the point where the applications running on these systems are generating real value for the end users.
Hello, everybody. I'm Krishna Palam. I'm the founding CEO of a startup. AcceleQuant is the name. Briefly, what we do is to accelerate the time to deployment of quantum hardware at scale for revenue growth. And we work with people who provide hardware. We also have now a fairly healthy customer pipeline. I must give a shout out since I see them in front of me. We're in the partner network, for example. One of the entities we work with is Quantinuum. And beyond that, before I migrated into this journey, I was an academic in the States for about 37 years, perhaps. And even before that, at IBM's research labs in Yorktown Heights for about 9. So that should carbon date me. So with that, I'll turn over the floor to...
Okay, so good afternoon, everyone. I'm Romano Rus. I'm the co-founder and also the chief scientific officer of Multiverse Computing. We are the largest quantum AI software company in the European Union, and I think that probably worldwide, okay? And we specialize in building software applications for industry use cases, okay? For by using quantum computers, and also on developing new AI tools, okay, based on quantum computing and also on techniques that are inspired by how a quantum computer works. So, we are already around 200-something people, headquarters in Spain, in San Sebastian, but we also have offices in many places, all right? And apart from that, personally, I'm also a professor of theoretical physics, but that's not so relevant today. Thank you.
Hi, everyone. It's great to be here. My name is Tommaso De Maria. I'm the CEO and the co-founder of Entropica. We are a software company based here in Singapore as well. And as you may know, in quantum computing, one of the big problems is actually errors. The fact that quantum computers usually don't work as they should. And what we are doing at Entropica is to build the software infrastructure for fault-tolerant quantum computers to automate and enable quantum error correction so the users and developers can actually use the machine in a meaningful way.
Thank you all very much. I think what is striking about the panel that we have here today is that you all come from very different angles, but we are all united in this ambition and in this firm belief to create value from quantum computing. So we have, with Tommaso, with Entropica, we have a company here that has started with NISQ, has explored NISQ, is now gearing firmly towards fault tolerance. With Roman, we have a company here that explores optimization as well as quantum-inspired solutions to optimize LLMs, AI models. With Krishna, we have here a company that was very difficult to research due to the fact that you are still in stealth mode.
So we've been successful at that.
Amazing. Yes, you have been very successful. Thank you.
At being in stealth.
Yes. And Joe, who has been the CEO of a company that from the very beginning has been quite firm on focusing on fault tolerance as the utility kind of era for quantum computing. And I would like to together explore the learnings that you had and explore why we at this point in time see a collective shift of the industry from NISQ to be expected to yield useful quantum computing to FTQC. And with that, I would like to start with Tommaso. You have been exploring NISQ. You have been then shifting to quantum error correction and to focusing on enabling quantum error correction. What were the key learnings in your view that have really prompted you and propelled you in this strategic redirection?
So you use the word shift for the industry, for Entropica. I don't know if I would go as far as calling it a shift per se. I mean, what happens with technologies is that the technologies evolve, right? And what people do is explore what is possible with the technology at each point in time, while they also map what the expectations for the technology grow, what that could be, right? So for Entropica specifically, the goal that we always had was to build software infrastructures that would make quantum computers accessible to people. And we spent quite some time at the beginning looking at, as you said, I wouldn't call it NISQ per se, because we were looking at algorithms that you could actually run on the existing machines. And I think is an important distinction there. And the reason why you spend time doing that is because since the technology is in constant evolution, it's really important as a company to actually understand how the machines work and how they operate, and also to understand what the limitations are by running something on the computers. And having a set of algorithms and techniques that give you a way to actually test the performance of the machines is incredibly valuable, because it really helps you to then go and map on the longer term what we need to fully, to get to a situation where quantum computers can actually outperform classical computers on applications. So I could go into the details of what we have learned, but I think just for the sake of time, for us what was really important is to spend as much time as we could by running computations on the hardware and really understand what is possible, what is not, and what we need to move forward. And I think the industry has done the same.
Yeah, thank you. I love the emphasis or the phrasing that you placed here, which is we're talking about an evolution here. So we have been learning through our exploration of the early stage quantum devices, basically up to the devices that we have nowadays. And we have then, based on these learnings, managed as a field to reprioritize. Now, with multiverse computing, we have a company that has already been tackling optimization problems, partially with a scope for quantum-based, let's say, advantages, but also based on possibly quantum-inspired approaches. So how far does that perspective of having learned from an exploration of the quantum space how far does this perspective flow into you having developed solutions that are perhaps competitive nowadays?
Yeah, actually that has been fundamental, because now a good part of what we are doing is AI inspired by how a quantum computer works, okay? And therefore we are using tools and techniques that we know because we come from quantum technologies, okay? Whereas the people from machine learning science and so on, and computer science, they use a different sort of techniques, okay? They don't know all these, no? All these tricks, all this language that we're using that comes from quantum computing. We learn how to use it also for machine learning and how to use that to improve actual classical machine learning, but inspired by quantum, no? And for us, it has been fundamental. It has been fundamental. So I always say the same thing, but it's true. I mean, the people from computer science and machine learning, they have a different toolbox, okay? And they can do many things, but they cannot do what we are doing because we have a different knowledge, okay? So for us, it has been instrumental, and it has allowed us, it's one of those very nice cases in which you are, investing a lot of time in understanding and doing something on, let's say, build a quantum computer, build quantum algorithms, and so on. And in the process of doing that, apart from developing quantum algorithms for NISQ devices and for fault tolerant and so on, in parallel to that, we also learn how to improve classical algorithms, which is a super nice byproduct because it has applications right now. So this is a perfect example of why one should think about problems that perhaps they are very far away, because in the process you may learn things that are unexpected, okay? This was completely unexpected to us, and it was a very simple example of something that we can do right now.
Yeah. So maybe you have in a way taken your angle of coming from quantum in the crudest formulation of it, and taken that to innovate not just in the quantum hardware-specific space, but also in perhaps the classical optimization, quantum-inspired optimization space.
Correct. Yeah.
For Joe, you have always been confident in the vision of fault tolerance or fault-tolerant devices being where we can expect utility-level quantum computing at a point where the dominant narrative was revolving around earlier devices, let's say noisier devices. Where did you take that confidence from when the consensus of the industry was shifted or was centered at a little bit of a different point?
I mean, there's nice ways of answering this, and there are not so nice ways of answering this. I think there was, to less of an extent now, but I thought there was a mass delusion around NISQ. It was driven by the power of wishful thinking, that you think, well, okay, we don't know exactly how the algorithm's going to work, we're just going to guess it, and then we're going to use stochastic gradient descent to try to train our quantum algorithm like we train a neural network. And the reality is we've known about neural networks since 1943, and it has taken more than 70 years before they've gotten to a point where they're delivering real results. So the problem, for me at least with NISQ, is that you don't know where the quantum speedup is coming from. Not really. I mean, you can talk about, yeah, it's moving in a different landscape and so on, but the real problem of that is understanding the landscape in which you're moving and doing this optimization, and generally people don't know. For any given problem, people don't really know how hard that particular instance of that problem is going to be. So at least from my perspective, if you cannot prove that there's a speed up, there probably isn't. When it comes to quantum algorithms, yeah, we know of algorithms where there are enormous speed ups, but these algorithms are all structured. There are things like Shor's algorithm, where you're using quantum Fourier transforms, you're using period finding, you're using techniques that you understand what they are doing. And at least my focus has been on trying to get to a point where we can use these techniques more widely to tackle a wider variety of problems, but where we can prove there are real speed-ups. So at least at Horizon, our focus has been on trying to build a pathway to automate the acceleration of conventional code on quantum computers, and that means taking elements of these algorithms that we know how they work and trying to apply them in an automated way so that we never make things worse. It's not like switching to a different optimization algorithm where some problems get harder and some get easier, but rather manipulating the code in a way that we can prove it always gets faster. So that's what my focus has been on. I try to stay pretty grounded. I like what Tommaso said about the need to be close to hardware and the need to understand the capabilities of hardware, what's possible and what's not. So I mean, you've some experience with this yourself, but we've become one of the first software companies to own and operate our own quantum computers. So we have one in our office here in Singapore. It's a relatively small system, but it allows us to integrate directly with the control systems so that we can get better and better control over the physical hardware.
Interesting. So a unifying factor between two differently angled companies is the need to stay close to the hardware innovation. But I like the distinction, it is interesting to point out here that your motivation or strategy came from a very theoretical approach of really having proven speed-ups that go way beyond what the near-term speed-ups could possibly be, at least on a derived level. And then really pushing the exploration and the enablement of that.
So there's this quote from Richard Feynman, and it goes something like, you must never fool yourself, and you are the easiest person to fool. Yeah. And actually that's more or less one of the principles of our company. It's slightly reworded, but at least I'm driven by that. It is so easy to get caught up in wishful thinking and get completely misled into a dead end. So at least from my perspective, it's important that we always understand where we're going, that there is a viable path that we can push forward on.
For Professor Krishna, it is, I think, quite interesting. The companies that we have on the panel have been around since 2018, 2019, have been going through quite an evolution. For you, you are coming in quite fresh as a new player into this field. based on the narratives that I have heard, tackling and confidently tackling optimization problems at a point where the field is discussing this transition, what kind of algorithms to focus on, what kind of hardware benchmarks to focus on. How easy is it for you to actually situate yourself and situate the focus of your innovation amidst such a mobile field?
Right. So technically, we are about just over 3 years old now, of which 2 were a real company. Before that, it was really a small group. There are 4 dimensions. I think Joe brought up a 4th one, which I'll comment on. The first three are obvious. There is this ongoing complaints, and depending on, to paraphrase Joe, how nice or not nice you want to be, about whether qubits are useful or not useful. Second, how many are necessary and how many are not necessary. And we can't, some people just espouse you need 10 million qubits before you do this without really understanding the problems. Third is what you're talking about, workloads. Fourth, the point that Joe brought up, which is very interesting, is this notion of understanding some abstract mathematical level that the gains are real. Now, you can't prove a theorem about everything, but having those guardrails is helpful. So we do all 4. So the company does 2 things. It has a foundational group that we haven't published yet because of the stealth. But what we do is, if you really want to get technical in computer science side of quantum, there are complexity classes called BQP, easy quantum, QMA, hard quantum. We essentially have a structural understanding of the complexity classes in that space. And then our guardrails guide us to work from there, the kind of structure that Shore is a special case of this framework. And building on that, the broad framework to operate. The rest is really amazing engineering by the guys in the company. That last 10 to 15% takes you from being commercially meaningful to not. So we do 3 things. 1, we have the guardrails. Within the guardrails, we design product. We are able to park problems that are extremely large. I can't say more today because of IP issues. We can take a billion variable matrix and run it to a solution, and this is a customer problem, on 120 qubits. So there is something we call an amplifier, where these things we call A qubits, acceleron qubits, can be many, but there's technical ways through which you can reduce the need of the footprint. Second, the point that was discussed, the last part, which is very relevant, touching the hardware. If you have that layer, depending on how good or bad the hardware is, you'll touch it more or less. So we have expertise in the company that can look at that layer and essentially denoise it, if you will. One of the words people use for a particular form of it is mitigation, and we do a lot more of that. So on today's machine, and I'm happy to mention the 2 companies we work with that I can talk about because we've signed off on the paperwork, IBM and Quantinuum. We essentially can deliver customer solutions at scale. So these are the 2 ideas. Solve the problem by having this small footprint, handle the noise algorithmically, not case by case. Now, in between comes the algorithm, the thing that you actually solve.
Yes.
For supply chain and logistics, it's optimization, gradient descent, or any variety you want to talk. And we have our own algorithms.
Yeah.
We are now, in about 8 weeks, likely to announce that we have replaced that layer for training transformers, a variety of deep nets.
Right.
So training time reduction, parameter size increase. So the key thing is you can simultaneously solve larger problems faster.
Right, so both actually for you and for Multiverse, we are looking at quite high ambitions also for the enablement of enterprise level solutions that are already being communicated nowadays. So and you also mentioned the aspect of talent here, you mentioned the aspect of having a team that is able to denoise today and will probably and hopefully also be able to do something adjacent tomorrow. How straightforward do you expect the translation of the use case, the value, the IP that you have today for today's solutions to be for the technology we have available tomorrow? Or
So, in a sense, what you're asking me is, the portability of these algorithmic modules horizontally across hardware platforms as well as across verticals, across applications. The lowest level and the highest level are generic algorithms. They live in this BQP framework or QMA, somewhere in between. So these are techniques that are naturally parametric. They're not dependent particularly. And then there is engineering. So for optimization, you tune the solution. And now this is a software, quantum software game. In machine learning, it's different. But the lowest level tends to be mostly agnostic, in the sense that the hardware-aware noise, denoising layers tend to be not as sensitive to where the inputs came from. So those are totally generic. The reduction module is generic. The algorithms that do a particular job, optimization, etc., are specific to verticals in our case.
So if I can add a little bit of color to what you said. So for us, it's also fundamental, and one should not forget that the final user doesn't know anything about quantum computing. Okay, yes. So here we are talking about quantum hardware, doing quantum software and so on, but we are not doing quantum software for physicists. That's not the goal, okay? We are doing quantum software for the masses, for your grandmother, for everybody, okay? And people, if you go to the people in the street, on average, they don't know anything about quantum computing or quantum mechanics or anything. They just want to use a solution, okay? It's as you use a car, but you don't know anything about mechanical engineering. You just want to use the car to drive, okay? So something that is fundamental is also to build solutions. And this has nothing to do with physics. It's more about engineering and product and market fit and so on. We have to build solutions that are easy for the people. Okay, you don't have to tell the people that they have to do, I don't know, which unitary rotation in which, no. They just know that they have a problem, and you have to provide them the solution in the most completely simple way, okay, so that they can just solve their problem, and whatever is happening behind, they just don't know. Okay, so it's super important to provide solutions as simple as possible.
Yes, to in a way abstract away from this kind of quantum expertise to really utilize the hardware. On that note, we can see that a lot of programs are now being geared towards quantum-specific kinds of degrees. We develop a quantum master's program in various geographies, PhD programs. We are ramping up the support for that. Do you expect that these quantum-specific programs are needed to drive innovation and value in the long term, or do you equally see that perhaps other verticals will actually make these kinds of key contributions, coming from the angle of AI or other technological fields?
Yeah, I think. Oh, sorry. No, just very quickly. I think everyone is needed. Okay, so we obviously need quantum engineers that have done, all the master's programs, PhDs, and so on. But we know, and I know from experience also, because in our case, we're also hiring AI people and computer scientists, mathematicians, and so on, which provide a different angle. And my feeling is that we are going to be needing AI specialists on top of quantum technologies, for sure. Yes.
Yeah, I think that's very key. AI, so there's quantum for AI, but there is AI for quantum. Think about it that way. AI for quantum is already there, for example, even in our company.
So I would probably approach this a slightly different way. I kind of agree with what Roman said, that we really do need all types of people. I run a software company. We build software development tools. The goal of what we're trying to do is to abstract away the quantum physics so that you can program in conventional languages. But in order to get there, we need a bunch of people that are experts in quantum computing. We need a bunch of people that know a lot about quantum physics, that know about the shape of a microwave. I need to send down a particular wire to control a particular, qubit on a chip. So we need those expertise. And I think as we look towards those expertise, we need to be really careful that, particularly in Singapore as a nation, that we don't get pushed towards the low value end of the quantum chain. What I mean by that is if we get sucked into becoming reliant on libraries that just solve particular optimization problems or something like that, and we view this as quantum education, that really does not get us to the high value end of actually building these systems, being able to build the algorithms that run on them, being able to build the firmware and the middleware in between, being able to build the control systems and so on, and that's where the real value lies. So at least from my perspective, when we think about these quantum programs, we need to think about that. And then when it comes to AI, what I would say is that although we look at the world and we see AI is really having tremendous successes, these kind of LLM-based agentic systems are having tremendous successes across a whole range of different domains of knowledge, they are not good in quantum yet. And you might ask why they're not good at things like quantum algorithms. And although they can tell you how a particular algorithm works, they are not good at creating new algorithms. And one of the reasons for this is because it's hard to come up with quantum algorithms. And humans don't have an intuition for how quantum mechanics works. We don't encounter it in our day-to-day lives. So the way you get good at quantum algorithms is by banging your head against the wall for 10 years, trying to figure out a solution to some problem. You try 100 things that don't work, you find one thing that works, and then you write up that one thing that works, and the one thing that worked is the only bit of training data the LLM gets. It doesn't get to see the 100 attempts that failed. We just don't have the training data for them to get good at this yet. Now, maybe we will get to better agentic systems that are able to generate all the negative results as well and learn from them, but that's not where the current state of the art is. So as things currently stand, in quantum computing at least, AI is not yet ready to take over from humans.
Yeah. What I like about...
Can I add one point to what Joe was saying? I would like to reinforce actually the first part of what Joe just said, how it is really important for companies like, well, certainly for Entropica, but I would say for all of us, to have people who have a very deep understanding of what quantum computing is and what needs to be built. Like, it is easy to, I have heard multiple times in other situations, people saying we can easily transfer knowledge from classical computing and start building software for quantum computing as well. And that doesn't sit quite right, at least with our experience. Back to the importance for Singapore to focus on very deep education, or at least to develop skills that are required in quantum computing, not only at the superficial level, but ideally at all levels required for the quantum computing industry, for the technology. Because something we have seen in Entropica, something I've really seen firsthand is how the more time you spend building software for the machines, the more specialized the knowledge that you need in the company becomes, right? So you start with knowledge on quantum information and quantum computing, and now we are expanding to system engineering, the hardware requirements for quantum and classical systems, and that is really deep, profound knowledge that is actually quite rare to find anywhere globally. And that is what you need, back to your question about how do we build a workforce in a way, that is what you need for the industry, and specifically is what we need in Singapore as well.
Yeah, which is interestingly tying back to this very reasonable yet persistent commitment issue that we collectively have as an industry, having a lot of promising modalities with a lot of very different long-term roadmaps, right? So if we were to have a singular architecture, we could perhaps bundle efforts towards the algorithmic development, the software development, bundle a certain kind of expert or domain knowledge. But what you're saying is the forced diversification of our portfolio right now just scarcifies some part of the necessary talent to make this progress towards.
I think also part of what I'm saying is that for quite some time, and maybe it ties back to what you were asking, there has been an incentive to look for the use case of quantum computing, these magical applications that would quickly bring the industry to a point where it becomes mainstream. And back to wishful thinking, that is wishful thinking. I mean, it might happen, but to some extent it is wishful thinking. We need to build the technology, and we need to make it accessible and useful for everyone.
Could I
Yes,
jump
please.
in on that? Just, I agree very much with what Tommaso has said. And, just to frame this, it's a little bit like, if we had perfect quantum computers tomorrow, if we had fault-tolerant quantum computers, it's a little bit like getting a server or getting a laptop or something like that with no software on it at all. And trying to jump straight to applications. And for a lot of people, the solution to this is saying, okay, bring your problem to us. We've got 100 engineers in a room. We're going to sit down and we're going to write a solution to your one problem in machine code. And that's not a very sustainable way for the technology to progress. So we need to be able to build up the abstraction layers. So I think a little bit in relation to what Krishna said and so on, that at a high level with quantum algorithms, sometimes you can write them in a way that is independent of the hardware below them because the compilers on the way down take care of that abstraction for you. And if you look at the way software is developed for computers today, for conventional computers, there's a lot of abstraction that comes into that. There's a lot of system services provided by the OS layer. There's a lot of abstraction provided by the programming languages and the compilers as you go up. And you get to a point where you have compiler frameworks like LLVM, where you can write a program in any number of languages. You can compile that to the LLVM intermediate representation, and then you can compile that to target basically any backend. So the compiler infrastructure is taking care of a huge amount of abstraction for you, getting you to the point where you can write very portable code. You can think about problems. If you're writing code in Python and MATLAB, anything like this, you're not thinking about how do I shuttle around bytes on my processor. Instead, you're thinking about how do I manipulate strings and matrices and other things like this. You're thinking about things much more at an abstract information level, about abstract data types and how you're manipulating them, rather than the kind of low-level concrete instantiation of this processing on the device in front of you. And we need to build up that abstraction in quantum computing if we want to get to a point where the technology fully lives up to its potential.
I think this is also the overall undertone of this development towards fault tolerance, that we form momentum around the growing abstraction, the growing agnosticity towards different hardware. Of course, there are then two parts to this that make the problem more difficult. One, again, the diversity of hardware, so just the effort it takes to abstract for all the different kinds of architectures. Tommaso developing quantum error correction codes by itself for just one modality is a huge task. For all of them, let alone for all of them. On the application layer, reflecting on the early days of quantum computing, we also tackle so many different use cases. We have heard about grid optimization problems, supply chains, material science, chemistry, meteorology. There is a huge range of applications we assume quantum to become relevant for. But now what I've been hearing from numerous conversations with this field is that we are gearing towards chemistry or a certain kind of application awareness towards chemistry. And I invite you here, please, to add on to be a use case where we can see quantum to really make a difference, or quantum compute to really make a difference. Do you think that this increasing application awareness here, or potential application awareness, introduces a simplification, a helpful simplification to the software development layer, that you will focus on more specific kinds of innovations?
Did you have somebody in mind?
I actually would love to hear all of your responses, so please take it away.
So I want to pick up, it's a natural segue from what Joe was saying about abstraction. I lived in this programming language compilers area, both in the high performance computing and in the embedded computing for about 15 years. And that's crucially an important part of how to scale the entire community, but more importantly, for all of us, if you think of ourselves as companies, which we do, revenue, and therefore business. So we have a slightly more, let's say, nuanced attitude towards how we declare a success. We call it quantum commercial advantage, which means there are two goalposts. The first goalpost is customers are willing to buy in, use it, and make money for themselves, therefore they pay you. Second is absolute wins, which won't go away over time. And we're looking at both goalposts, just being pragmatic. But given that to be the case, the type of use cases which go beyond use cases now, because they are now customer revenue generating use cases, think of it that way, those have come in two flavors. One, not as ambitious, not as grand, but short term, which are working. And the grander ones like be it battery chemistry or drug discovery or personalized medicine down the horizon. Now, the ability to scale this across these domains does require what we used to call as researchers PL&C, programming languages and compilers kind of culture, and that's crucial as it goes horizontally. But nevertheless, industry has always grown, and we are in that stage where you scale based on enough revenue generating verticals. So as I mentioned, I was at IBM for the first 10 years of my life, and they had a very focused initial eye on Wall Street, to a point where it was such a focused eye that they lost out the PC revenue completely. They just lost the PC game. So being able to be nimble is good and great, but it need not be a solve all for revenue in the early days. That's my point. You don't have to be good for every vertical, but having that roadmap is fantastic, and aspiring to be on the roadmap, these abstractions are key.
If I may add, I think since you mentioned the example of chemistry and also molecular simulation and so on, it's very interesting. It's true that if we have chemistry in mind or material science, we can develop tailored algorithms only for those specific applications. And chemistry is kind of very popular in the people of quantum computing because it looks as if it's going to be one of the first applications of a quantum computer to simulate molecules, to simulate materials, for the development of new molecules, development of new drugs, new vaccines, and so on. But personally, I think that's a misunderstanding, okay? So the fact that molecules are quantum doesn't mean that they are easier to simulate with a quantum computer, okay? Because the problem is that molecules are not made of qubits, they are made of fermions, which is a completely different quantum system, and it's also very hard to simulate even if you have a quantum computer. I mean, eventually we'll do it, but I don't think, this is just my personal opinion, I don't think that's going to be the first application of a quantum computer. I think there are other applications that are going to come first that require less resources. We'll simulate molecules, for sure. We'll simulate materials, which, by the way, are also made of electrons, okay? But before that, we are going to find other applications, say quantum machine learning, for instance. I think that's going to come first, okay, before we are able to simulate molecules, let's say organic molecules that have, I don't know how many atoms and electrons, okay?
Yeah, I mean, when you say quantum machine learning as a first application, there's, of course, a vast potential areas of application.
Yeah,
so could you be more specific?
It's not that, quantum machine learning, I mean, let's say quantum AI, okay, quantum neural networks and so on, large language models assisted by a quantum computer, okay, that could be improved using variational quantum circuits. I think that's going to be an application that's going to, it's naturally encoded into qubits, okay, and I think that's an application that's going to come first for two reasons. First, because I think that the machines that we have, even if they are not error corrected, they could already be useful for that, okay? And second, because there is such a huge trend in AI nowadays that it will be difficult to find, difficult not to believe that there's going to be a direct application right away, yeah.
Can I jump in on that one? I have to strongly disagree. So the problem with a lot of the near-term quantum AI, the kind of variational techniques, is it's very, very difficult to prove anything about their complexity, about how easy it is to apply them, how readily they will be able to learn things. Basically, the situation you're in is you have to just try. And that makes it very difficult to say things for certain. And this is true of classical machine learning too. There's, classical machine learning is basically the art of just trying, and learning theory is like proving theorems about it. And when you go down the learning theory route and start trying to prove theorems about it, you prove it's impossible to machine learn anything, and that turns out to be wrong because the real world doesn't look like the idealized distribution you come up with. So, in quantum machine learning, to know that we have real advantages, if we're in the near-term version where we're using variational techniques, then we're in a situation where we have to just try it and see, more or less. Once you go towards kind of more structured algorithms in the future, yeah, we can prove you get speed-ups for certain machine learning algorithms, and you can analyze the algorithm, you can prove there's a speed-up. But what's really nice about chemistry is we know that you can simulate all of chemical dynamics efficiently. All of molecular dynamics are efficiently simulable on a quantum computer. And yes, there is some encoding overhead for dealing with fermions, rather than qubits. But I mean, that's just the anti-symmetric subspace, so like it's not too bad in terms of encoding, and it's efficient. Now, a lot of people that work on quantum chemistry, quantum chemistry is something different, work on quantum computing for chemistry, are focused on spectra, on like determining the energy of the lowest lying state. And that's actually a hard problem. That's one of these QMA complete problems. So it's harder than quantum computers are believed to be able to solve. But the nice thing is that chemists don't actually need to know this. They think they need to know it, but they're wrong. And the reason they don't need to know it is because they cannot access it in the lab. When you have things that are spin glasses and other kinds of constructions like this, they do not cool. So you do not see the ground state in the lab. That's also why you can't solve them efficiently on a quantum computer, because again, they don't cool. It's hard to access the ground state. But all of the stuff you can observe in a lab is necessarily governed by dynamics, and those we know you can efficiently simulate. And that's a place where there is a big advantage for quantum computing over conventional computing.
If nobody else has a comment, I'm happy to jump in.
Yes, please.
So there is quantum advantage and there is quantum commercial advantage. And what I like to say here in response to Joe's comment, yes, chemistry is indeed a very lucrative area to be after. It's not a question of, I guess, whether, but when. So in that sequence, speaking of machine learning, and he did pick up the difference on those two items. One, whether you just run some sort of an iterative solver, VQE, your favorite one. But he also mentioned if you were to design from first principles a quantum-specific algorithm, and that's what we do. And we are able to classify it in this whole BQP QMA hierarchy and be able to solve it. It's just that we don't publish and do this with demonstrable, measurable results. But there, the issue is not about proving necessarily. It's also an area that all this compiler work and optimizing compiler work thrives on and thrived on, benchmarking. So you need to just have credible benchmarking.
Yeah, I am happy that you brought up QML. We are lucky to have a very strong QML community here in Singapore as well. There's space, or I can see space for both of the responses here. QML is one of the applications, but also then, of course, chemistry as a provably simulatable system, with the open question actually being the firm timeline here. And I want to bring up a last notion, because I think this is our chance to maybe connect with clear things up for the audience as well. There was a recent paper by Jim Preskill and Jens Eisert on the term FASQ, fault aware. Please jump in.
I haven't read the paper yet. It's been in my feeds on like Twitter and everything, but I haven't read the paper yet.
It's basically
embarrassing admission.
Oh no, not at all. I haven't read it fully either. That's why I was asking. But it is about the notion of fault awareness. Fault awareness as an intermediate step between fault tolerance and this kind of NISQ era that we are in today. And you bringing up this timeline and you bringing up this gradual scaling towards these highly ambitious, universally fault-tolerant problems that we in between aimed to address as the next step. How much do you think could this new notion reconcile the gap between what we have today and what we will have in 10, 5? Give me the time, years.
To be honest, it's a very difficult question to answer. I haven't read the paper either. So it's good you bring it up. The short answer is I don't know. What I can tell you is, so Preskill, just for the audience, he also he came up with the concept of NISQ, right? So I think what Eisert and Preskill are doing is really useful for a community, because they are trying to codify the different stages of quantum computing as the technology evolves. I don't know if it's really conducive to try to map that to any realistic future timeline or the evolution of of the technology. I'm not able to answer the question on the spot. I think the value of these papers, of these publications, is that they crystallize the capabilities of quantum computers at a point in time. And then what we can do, we can go back and look at how things have been evolving, and that gives you a very clear perspective of how quantum computers are advancing really, really quickly, because the NISQ paper, if I'm not mistaken, came out in 2018, if I remember correctly. And today is 2025, it is only 7 years, which is in the lifetime of quantum computing, I would say, is a very short period of time. So I'm not really answering your question directly, but what I'm trying to do here is to appreciate how things are evolving really, really fast, how new concepts of quantum computing capabilities are emerging pretty much all the time. And I think it's important to appreciate that, especially as we approach fault-tolerant quantum computing in terms of capabilities.
Yeah.
Maybe as a quick remark, I think this paper is important to understand what's going on with the hardware, but from the software perspective, nothing changes. I mean, because we need to be developing the same software applications, either if it's for NISQ, for fault-tolerant quantum computers, or for fault awareness machines and so on. It's exactly the same, okay? The better the machine, the better is going to be the performance. But if you have an algorithm that is working for NISQ, it's going to work even better for a fault-tolerant quantum computer, and so on. So from the software perspective, I think that it's just exactly the same. You can tailor things, it's true, but the philosophy should be that whatever you build now, it should be valid also in 20 years.
I should say, again, I'm taking the opposite side on this, in that I'm much more in favor of the few-shot algorithms rather than variational algorithms. And when you look at that, a lot of those don't work on NISQ devices. So if you're trying to do like eigenvalue estimation or any of these things with quantum Fourier transforms, they're fairly brittle, and individual faults can set them off. If you're able to do a certain amount of error detection in your computation, you can certainly get better results out of it. And as you move to fault tolerance, you get a whole new algorithms toolbox that you can make use of. So I would agree with Roman that like if you have something that works on this device, it's probably going to work even better on a fault tolerant device. But there are whole classes of techniques that don't work on NISQ devices that you need to get to much lower noise regime in order to take advantage of. And I think that's where a lot of the value of quantum computing ultimately lies.
Yeah, and knowing that you are basically building a compiler toolchain that really starts at the metal, and with that also has to respond to, for example, the need for hybrid classical quantum computing, so the real-time processing, for example, of quantum error correction codes, which is something that Tommaso Antropica has to deal with on an ongoing basis as well. That would lead to my next question, which is, in this kind of transition towards real-time quantum error correction, towards fault tolerance, or whatever words we find in between now and then, how much, or what do you see to be the challenges on this deep, low technical level to really master this integration for your particular cases?
I'm happy to take that. So we are getting to a point, especially since I saw the time, especially since you mentioned real time, we're getting to a point where the integration between software and hardware is becoming increasingly critical. And it goes back to what Joe also mentioned, the fact that even for software companies, having a deep, comprehensive understanding of quantum hardware, and when I say quantum hardware, I don't only mean the qubits. I mean all the architecture that sits around the qubits, decoders, controllers, classical computers, GPUs, FPGAs. I think the biggest and most beautiful challenge is how do you start controlling multiple computing hardware architectures in a way that allow you to actually extract value from the quantum system itself. And that is a challenge that lies both in hardware, because everything needs to be integrated very tightly, and in software, because the software ultimately is what is going to drive the integration, it is what is going to drive the functioning of the hardware. So that is really where one of the biggest challenges moving forward lies.
Okay.
I think we're out.
With this, I believe we are out of time. I want to thank you all very cordially for the honest perspectives, the diverse perspectives that you have brought to this panel. I'm looking forward to all the follow-up conversations that we will have over the course of the Switch conference, and hope you will learn as much as we in the audience did today.
Thank you.
Thank you very much.
Thank you.
Thank you.
Thank you. Thanks, everybody.
And a very big thank you to our moderator. Can we hear for Dr.